Hi, welcome back. So we're going to pick it up from where we stopped last time, which is we had defined the average current going through a cross section of a wire. So remember the formula is the average current is delta Q over delta T. Um, so the simplest type of problem you might have to deal with is something like this. That's very, very easy. If a total charge of 3 Coulomb goes through a cross section of a wire in 5 seconds, what is the average current? Well, delta Q, that's the amount of charge, so it's 3 Coulomb here. It went through, it took 5 seconds to get through the cross section, so delta T is 5 seconds. So the average current is 3 Coulomb divided by 5 seconds, so it gives 0.6 Coulomb per second, which we know is the same as 0.6 ampere. Okay, because 1 ampere is 1 Coulomb per second. Now notice because the charge and the time were given with 2 sig figs, I gave the current with 2 sig figs also. Okay, so that's a very trivial example. Now things can get a bit more complicated. Sometimes we're given a function q of t. So what does it represent? A function q of t gives the amount of charge going through a cross section as a function of time. So it tells us how much charge goes through the surface at any given time. Okay, once you're given that, you can be asked to calculate an average current. So how do you do that if you have a function? Well, whenever you're asked to find an average current, you have to be told between what time and what time. You have to be specified 2 times. So the average current between 2 times, let's say time t1 and t2, is given by the following formula. By the way, here I assume that t2 is after t1. So I could have used, instead of t1, I could have used t initial, ti, and instead of t2, I could have used t final, tf. But let's use t1 and t2. So if you have a function q of t and you want to find the average current between t1 and t2, well, you still use delta q over delta t, but because you have function q of t, you can calculate delta q in the following way. It's simply this. The average current between t2 and t1 is the value of your function q evaluated at t2 minus the function q evaluated at t1 divided by delta t, which is t2 minus t1. Okay, so you just plug in t2 in your function q of t, t1 in your function q of t, and you calculate this ratio here, which of course this can be written also this way because t2 minus t1 here is just another name for delta t. Okay, so we'll do an example in a minute, but it's pretty straightforward. You just plug in the values. But again, notice that if you're asked an average current, it's always between 2 times. You cannot talk about an average current at one time. You have to be told, you have to be asked the average current between what time and what time. Okay. Now, current is a bit like think of mechanics where you have an object moving with a certain velocity. So you can think of current as a bit like velocity of an object moving, and q would be like the position of an object. So you can have an object, and if you know its position as a function of time, you can calculate the average velocity between 2 times. So for the average velocity between 2 times, you calculate the position at t2 minus the position at t1 divided by delta t. So that's the same thing we do here, although the meaning is different here. We're not calculating the velocity of the charges. We're calculating how much current is going through a cross section. Okay. So, but like in mechanics, when you calculate an average velocity of an object, you can also calculate the instantaneous velocity at one time. So here we can calculate the average current between 2 times, but we can also calculate the instantaneous current at one specific time. And how do we find that? Well, in mechanics, to find the instantaneous velocity, you do the derivative of the position with respect to time. Here, to find the instantaneous current at one time, we do the derivative of the charge, q as a function of time. So it's a derivative. Okay. If this is a bit abstract, don't worry, we'll do an example in a minute. Now, like in mechanics, if an object moving, the average velocity between two times is not necessarily the same as the instantaneous velocity at some time. That depends if the object is speeding up, slowing down, and so on. But in mechanics, there's a special case where the velocity is constant, and that means that and that's a special case of motion. Same thing here. There's a special case of current, constant current. So that what that means in our case is that if you look at the flow of the charges, if the current is constant, it means that the flow of charges is constant. The charge don't speed up or slow down and so on. They just move at a regular rate that is constant, at the constant flow through the wire. Now, if the current is constant, then there's several consequences to the equations we just saw. There's several ways, there's several statements here that would be all equivalent. Okay? There are different ways of expressing the same thing. If the current is constant, you can say the following. First, if you look at the average current, when the current is constant, the average current gives the same value for any values, I should say, any values of T1 and T2. So if you do the average current between 1 and 5 seconds, or the average current between 2 and 8 seconds, or between 1.36 and 5.67 seconds, you always get the same answer for the average current when the current is constant. Okay. Also, when the current is constant, the average current gives the same value as the instantaneous current. Okay, that's pretty obvious. So whether you use this equation here to calculate the instantaneous current, or you go back and use the average equation, when the current is constant, you get exactly the same value. And the other statement is also pretty obvious. If the current is constant, then that means that this I of t in that equation here, when you calculate dq dt, when the current is constant, what you get here for that side would be just a number that does not depend on time. So there will be no time here. Once you differentiate q of t, you get a pure number, like 5 or 6, okay? And there will be, and what I mean by that is that there's no time dependence. So there will be no powers of t, t squared, t cubed, 1 over t, log of t, sine of t, anything. It's just a pure number. That's when the current is constant. Okay, just a little quiz. We get back to that in class. But as a question, if I tell you that in a certain circuit, the current is constant, what can you say about the function q of t? What is the most general function q of t that when you differentiate it, you get a number? So no time left. In other words, what is the most general form for q of t that gives a constant current? This is quite a bit subtle. So if you don't see now, don't worry. We'll get back to that in class. We'll play with that, okay? But that's a challenging question. Okay, now we are ready to do an example. Let's start with an example where q of t is given by this function. So q of t, you have a certain wire, and you're told that the charge through a cross-section of the wire is described by this function q of t, 3t cubed minus 4t squared plus 8. Now, right away, you look at that, and there's something strange here, because q must be in Coulomb, so this must be in Coulomb. But if you look at this, 3t cubed, what are the units of 3t cubed? Well, t is in second. So when you cube a time, you get something in second cube. So this number here, because you have a t cube, is in second cube. That's not in Coulomb. So the units of this don't match the units of that. Here, 4t squared, you square a time. So 4t squared would be in second square. That's not the units of q, so that doesn't make sense. And finally, 8 here has no units. So the units here are all totally wrong. Now, people, the reason for that is that when we write that, we're cheating a little bit. Now, if we don't want to cheat, we have to add something like this, which we don't always write, but it should be always written. Here, it means that we add where in that equation the charge here will come out to be in Coulomb if for t here and here you use a time in second. Okay, so that tells you you're safe with that equation. Plug the t in seconds, the q will come out in Coulomb. But that's still weird. How can you get a q in Coulomb when the t is in second? What we really mean is this, okay? And people don't usually explain that, but it's important to understand. Really, what we really mean is that the units of the constant in the equation are not shown. So that's where we're cheating. When you see the 3 here, the 3 here really has some units. The 4 has some units, and the 8 has some units, but we don't show them. So really, if you write the equation with all the units shown, here is the correct equation, the full equation. What happens is that the units of the 3 here must be such that when you plug a t in second in the cube, the t cube here, you get Coulomb. So look at this equation here. Okay, look at this. When t is in second, t cube is in second cube. So the 3 here must have just the right units that when you multiply by a time cube, you get something in Coulomb. So the 3 here is really in Coulomb per second cube. Okay? So if you plug t equal 5 seconds, t cube would be in second cube. The units of t cube would be in second cube. The units of t cube cancel a second cube here, and you're left in Coulomb, which is what we want. Same thing here. We have 4t squared, but the 4 is really in Coulomb per second square now, so that the units of the second square here cancel the unit of the t square, so you get Coulomb again. Finally, the 8 here must be, now there's no factor of t, so the 8 must be directly in Coulomb. So each term here is in Coulomb after you plug in a time in second. Okay, so by this equation here, we really mean this. Okay, make sure you understand where the units come from and ask me in class if it's not clear. Okay, but this is quite ugly, so usually we don't bother writing all the equations and we just write this. Okay, now we can do a calculation. What's the average current between 0 and 2 seconds? Again, keep in mind that when you ask an average current, you have to be told between what times, between T1 and T2. So this is 0 is our T1 and T2 is our is 2 seconds. So we calculate that. We go back to the definition. The average between 2 times, the average current between 2 times is the charge at the later time minus the charge at the earlier time divided by delta t. Okay, here I wrote the second here, but usually in the steps we don't bother writing all the units. So I have to calculate Q at 2 seconds. So I go back to the equation here and I plug t equal 2 seconds. So I get 3 times 2 cubed minus 4 times 2 squared plus 8. That's Q at 2 seconds. Minus Q at 0. So you go back here, plug t equals 0, you get 0 plus 0 plus 8. So you get 8. So you get Q at t equal 2 is equal to this parenthesis here, 3 times 2 cubed minus 4 times 2 squared plus 8. That's Q at 2 seconds. You subtract Q at t equals 0, which is 8, and you divide by delta t, which is 2 minus 0. And if you calculate that, you get 4. Now, finally, this is my final answer, so I give it to the right number of sig figs. I used 2 sig figs because my time here, 2 seconds, was given with 2 sig figs. And the units are Coulomb per second because it's a current, or amps. Okay? So make sure you can, with this function here, it's clear that you get this average current between 0 and 2 seconds. We can repeat the calculation. Here, this is the same question as before. I just copied here so that we see the function again. For the same function, what's the average current between 1 and 3 seconds? We just did between 0 and 2 seconds. But now we repeat. Notice that the delta t here is the same as before. Between 1 and 3 seconds, delta t is 2 seconds. We just did it between 0 and 2 seconds. The delta t was also 2 seconds. But we've changed the time. So what's the average current? We just repeat. You do a charge at t equals 3 seconds. You subtract the charge at 1 second divided by t2 minus t1. If you do that, okay, you plug t equals 3 in q of t, you get this, minus you plug t equals 1, you get this, divide by this delta t, you get this. Okay, I'll let you can stop the video if you want to check, do the calculation, but that's the final answer here, 23 amps. So notice, even though the delta t is 2 seconds like in the previous example, between 0 and 2 seconds, remember the average current between 0 and 2 seconds was 4 amps. Here between 1 and 3 seconds is 23 amps. So now we see that the average value is not the same as before. That tells us that for this function, the current is not constant because the average value changes. Okay. Now, now that we've calculated the average current between for 2 delta t, we can ask, okay, for the same function, again, I just repeated here so that you can see the function on the screen here. Now, what is the instantaneous current at 1 second? Notice, for an average current, you have to specify 2 times, but for an instantaneous current, we just specify at 1 specific time. Okay, like velocity, you can ask the average velocity between 2 times or the instantaneous velocity at 1 specific time. So how do you calculate that? You just take the derivative. Okay, now let me slow down a bit here. The derivative here, we do the derivative with respect to time of this function here. Now, in calculus, usually you work well probably with either f of x or y of x. Let's say you have y of x. This is a function you differentiate with respect to x, usually in calculus. So x is your independent variable and y is the dependent variable. And you can calculate let's say dy dx, right? You differentiate the function y of x with respect to x. Okay, so here we do dq dt. So instead of having y of x, we have q of t. This is just a change of labels, so there's nothing really deep here. But everything you've learned about in calculus, you have to repeat here. But you replace, whenever you were thinking of x before in calculus, you replace by a t. And the function here, that example q is the equivalent of y. So this is like if you had, let's say, function y of x equal 3x cubed minus 4x squared plus 8. And you differentiate with respect to x in calculus. Now we differentiate with respect to t. So it's pretty easy once you make the switch from x to t. Okay. Okay, so what do you get? So you differentiate that here with respect to time. Okay. Remember, when you differentiate a function, the constant here stays the same. So if you differentiate 3t cubed, what do you get? The derivative of 3t cubed, you get the 3 here that came from this 3 here, multiplied, I use a dot here for multiplication here, multiplied by the derivative of t cubed. So the derivative of t cubed is you bring down the exponent 3 multiplied by t to square. You decrease the exponent by 1, right? So this is the derivative of 3t cubed, which is just 9t squared. Well, it's written here. Okay, so that's where the 9t squared comes from. Okay, that's the derivative of 3t cubed. Okay, so it's like if you're in calculus, you'll do the derivative of 3x cubed. You'll say right away, you'll say derivative of 3x cubed is 9x squared. Okay, so the derivative of 3t cubed is 9t squared. Okay, same as before. Okay, now derivative of minus 4t squared. What is that? Like in calculus, you get minus 4, that's an overall constant, stays there. The derivative of t squared will give you 2t to the 1, which is just t. So the derivative of minus 4t squared is minus 4 times 2t, which gives minus 8t. That's this. Finally, the derivative of 8 is a constant. The derivative of a constant is 0. So really, if you want here, you could say, well, there's really a plus 0 here, right? This came from the derivative of the 8 here. But plus 0 doesn't do anything, so we usually don't even show it. So that's it. This is the derivative of q of t. So I did dq dt with that function here. dq dt gave 9t squared minus 8t. This gives the current at any time. But that's not what we were asked. We wanted the instantaneous current at 1 second. So then it's easy. You want the current at 1 second? Just plug in t equal 1 second in that equation here. You get 9 times 1 square minus 8 times 1. It gives 1. Or with two sig figs, 1.0 amp. This is the current at 1 second. Okay? So that's how you find the instantaneous current at any given time. Okay, so to summarize, if you're given a function q of t, you can find the average current between any two times, or you can find the instantaneous current at one specific time. So from q of t, we know how to find I average or I instantaneous. The next question is, what about the opposite? Let's say you're given I of t, the current, and you're asked to find the charge. Okay, so far we've went from the charge to the current. What about going the opposite way? You're given the current as a function of time and you want to find the charge. How do you do that? Okay, so first, so if we are given the function I of t, that's the current as a function of time, what we can calculate is how much charge is going through a cross section between two times. Okay, that's what we can calculate. So you know the current as a function of time, and you say, okay, if I take a cross section of my wire, I can calculate now how much charge went through between two specific time, t1 and t2. How do you calculate that? Well, you can guess it. See, if we add q of t, to find the current starting from q, we took a derivative. Now we want to do the opposite. We want to start from the current and get to q of t. So what's the opposite of a derivative? We integrate. We do an antiderivative. So since the current is a derivative of q of t, what you can do is that you can move the dt on this side here, and I switch the two sides. So I have dq is equal to I times dt. So dq is equal to I times dt. Okay, all I did is that I moved this dt here up here, and then I get this equation here. So if I want q, I have dq here. If I want q, this is derivative, so to get rid of this derivative here, I integrate. So I'm going to integrate, but I have to do the same thing on the other side, so I integrate both sides of the equation, and I get this. So the integral of dq is equal to the integral of I of t dt. But the integral of d something, integral of d anything, is just this function here, okay, which we call delta q, okay? So delta q, this is, I could have called that q, but delta q here is just to keep in mind what it means. This thing here is the amount of charge that went through a cross section between t1 and t2. So if you're given a function I of t, and you want to know how much charge went through in a cross section between 5 and 8 seconds, you have to do the integral from 5 seconds to 8 seconds of I of t dt. Okay, this is a bit more complex, and we'll do examples in class. Okay, so we'll pick it up from there in class, in next class. Thank you.